Hi everyone, today we are going to talk about how air conditioner works. So we're going through three things. First thing is thermodynamic, refrigeration cycle, and also the four major components. So to understand how actually air conditioner works, right, we need to understand the fundamental. We need to go back to the very basics, how cooling works, right? So thermodynamics is the fundamental principle of how cooling is achieved, right? So we know that heat flows from a hotter region to a colder region, all right? So for example, in order to cool a room, we need something that is colder than the room, right? So that the heat will flow from the room to the cold substance that we provided. Then we transfer that heat outside the room. We do it repetitively, then the room will eventually cool down. This is how the science behind cooling, right? And we know that there's a statement that heat cannot be created, or energy cannot be created or destroyed. So it can be like air conditioner does not produce the cold energy, right? It actually absorbs heat and throw it outside. In a sense, like it removes the heat from the room. That's why the room becomes cold, right? So the thing is, we need to do these things very efficiently, right? And we know that if we have this so-called material phase change, the enormous amount of energy can be carried from the room to outside, right? Because our objective is we want to remove, but we want to remove in a very efficient way, right? So I'm sure we have all learned about phase change, right? So this is the point that we want, right? The phase change process. You see, we know that from gas go back to liquid we call it condensation. Like condensation, air conditioner, how air conditioner works, we must talk about condensation, talk about evaporation, right? It actually is what it is about. It's phase change, right? So during condensation, heat is released, all right? Then from liquid to gas is evaporation. That means it's like boiling, right? You boil water, right? You're boiling. So heat is absorbed and then boil, right? So the thing is, we go deeper into this thing is, why don't we use water, right? We use water to absorb heat from the room, and then we transfer the water outside to reject the heat. Why don't we use water? You see, water we call it the boiling point, right? Boiling point at 0.1 MPa outside is really atmospheric pressure. So at atmospheric pressure, the phase change happened at 100 degrees Celsius, right? So the boiling point, right? At where liquid water turn into steam, vapor, right? So 100 degrees Celsius for us human, we can't do much thing because the energy level is very high. It's not practical to use water, alright? Because the phase change require a very high amount of energy, right? That's why over the year, engineer they created this or chemist or somebody created a chemical mixture called refrigerant, right? It's an engineered product. What's cool about refrigerant is, for example, R410A, the very common one, is at atmospheric pressure, the boiling point is actually like negative 50 degrees Celsius, right? Around there. Still, if you compare, both also is not useful because one is too much energy, one is too low, right? You open the refrigerant, it immediately turns into gas already. So it's not useful. So what if we know now temperature is a problem, all right? We want to control temperature. So we know that pressure and temperature goes together, right? Directly proportional. So what if we control the pressure, we can control the temperature. So let's say we 10 times the pressure. With 10 times the pressure, you see water, you 10 times pressure, the boiling point goes even higher. So it becomes less and less practical, right? Start is already not practical, then we don't talk about the increased pressure, right? Refrigerant is different. If we increase the pressure by 10 times the atmospheric pressure, now the refrigerant boiling point, that means the phase change process is somewhere around 7.5 degrees Celsius. Now we are talking about something that is practical, useful, right? For example, you put this refrigerant inside a room, 7.5 degrees Celsius. So we know that heat flows from hotter region to colder region. So if the room, for example, is around like, I don't know, 28 degrees Celsius, right? You put something 7.5 degrees Celsius, this thing will become hot, right? It will absorb the heat, right? Just like a cup of coffee, it will always turn warm. So this thing will start to boil, like start to go through the phase change. Now, when we put, you see, go back to the question why we want the phase change process, right? You see, if 7.5 degrees Celsius or somewhere around the temperature is colder than the room, somewhere around there, maybe 10 to 15 degrees Celsius, whatever temperature that is colder than the room, if at that temperature, the substance is not undergo phase change, the temperature will gradually increase. For example, 7.5, you put this thing inside a room, it becomes 10 degrees Celsius, 15 degrees Celsius, 20 degrees. Eventually, it no longer has the, we call it temperature difference or the delta T to absorb heat, right? What happens? That means no longer useful. We want to extend the usefulness of this substance as long as possible. So we know that during phase change, energy is used for the phase change process instead of increasing the temperature. So that's why during phase change, temperature remain constant. That is what we want. We want the temperature remain constant so that it continues to absorb heat, right? So now 7.5 is the boiling point. You put the refrigerant there. The refrigerant will stay 7.5 all the way. Then during this process, it will evaporate, right? Slowly turn from liquid into gas until it fully evaporated, 100%, everything goes to gas, then it starts to increase temperature. At that point, we don't want the refrigerant anymore. We say, okay, refrigerant, you have done your job. It's time to move to outside, reject the heat, turn back into liquid, then come back, right? This is how we want the substance to work. So, now, another thing is, just now we talked about heat absorption, right? This is how we absorb heat. How about heat rejection, right? Why we need certain temperature? Because you see, outside, right, we say generally speaking, the outside temperature is around maybe 30 to 35 degrees Celsius. Alright, so you need something that is hotter than the outside air in order to reject heat, right? Again, heat flows from hotter region to colder region. You want to take away the heat from the refrigerant because the refrigerant absorbs heat, you want to take away, you need the refrigerant to be hotter than the outside air. So, we control this again. We increase the pressure after we absorb 7.5 degrees Celsius, right? We bring it outside, we increase the pressure. For example, 3 times, right? We increase 3 times, then the refrigerant becomes 45 degrees Celsius. Alright? It's still a gas form, but you increase the pressure, it becomes hotter than the outside air. Now we can talk about heat rejection, right? We bring an outside air, like the typical air conditioner. We use the outside air to cool down the refrigerant, right? So this is basically why we need phase change process and why refrigerant is invented and used, right? So now we know that we need something cold, right? Something cold, absorb heat and bring outside. So like this is a theory. So how, like human, how we're going to do it, right? How we're going to do the whole process, right? So it's like, we heard about we invented the refrigeration cycle, right? The refrigeration cycle, so it's compression, condensation, expansion, evaporation, right? So now this is a pH diagram, alright? Pressure and enthalpy, right? Enthalpy is H, they use a symbol. And enthalpy basically is like, you think of it as like heat or energy, right? So here, the y-axis is you go up, the pressure is getting higher, and here is the energy is getting more and more energy, right? So this is a 410A chart, right? Different refrigerant, they have different kinds of value here, because this represents the property of the refrigerant. Okay, so here we can see that here we have the horizontal line. From here to here is the pressure, but you see in between here, under here, there's a, what do you call it, temperature also, right? But here you see, as the energy increase, the temperature remain constant, right? Why is that? It is because phase change is happening. So area under this curve is where phase change occur, right? This here entirely is the phase change process. And you see temperature come until here and it drops down. If you see closely, this thing come until this line will drop down, because you drop down as you increase the energy, the temperature start to raise. Because here is, like we call it saturated vapor. Everything here is gas or vapor lah, right? Here is the phase change. During phase change is a mixture. You slowly turns from liquid to gas lah, right? And of course here will be liquid lor. So this line, they call it the saturated liquid line, right? That means everything is liquid lah. So you have unsaturated liquid. That means most of it is liquid, but still there is some vapor inside. So imagine you start from here, everything is liquid, then you start to increase energy mah. You start to give, for example, you boil the water, you boil it, it goes through phase change, alright? Start from 100% liquid, then maybe like 90% liquid, 10% gas, right? Then 50-50, like now 10-90 like that. Then eventually hit this point is 100% gas, 100% vapor. And this line, we call it saturated vapor line, right? So everything here is saturated vapor. So we have three color here, right? So this green color line is at atmospheric pressure. So just now we say atmospheric pressure, not useful, not practical. So we are not going to use this line. So now we push the refrigerant up to 1 megapascal, which is 10 times atmospheric pressure. Now temperature here, just now we say 7.5, right? So now how are we going to increase this 7.5 to like how are we going to 3 times the pressure, right? After we absorb everything, how are we going to move from this blue line to this red line, right? So that's why we need the first process, the compression process, right? We want to squeeze the refrigerant, right? We reduce the volume, we squeeze it, and we know the science behind. The pressure will increase, and so the temperature will increase, right? That's why we need the compression process, right? We squeeze the refrigerant so that it becomes hot, as hot like maybe 10 degrees Celsius hotter than the outside temperature, so that we need the delta T, so that heat can move around, right? Can move, can reject, right? Right, after we compress, right, we want it to turn back to the liquid, right? Because like we reject it, we only need to come back as original, then we do the whole process again, right? Because we need a repetitive process in order to cool, right? It's not like you turn on aircon, immediately one process, the whole room becomes cold, right? We need a repetitive process. So the refrigerant will undergo a condensation process, right? You see from here, if you look closely, actually the temperature will drop sharply because everything here is gas. So you take away the heat, immediately the temperature will drop. Then here again, you hit the point where condensation start to happen. So here you can see the temperature will be constant until it hit 100% liquid, right? Then at this point, the temperature is still very high because phase change from inside, outside also same. Phase change, the temperature remain constant, doesn't change, right? So 45 degrees Celsius, definitely we don't want to bring in inside the room. So again, we need to do the opposite. We need to reduce the pressure so that the temperature will reduce. That's why we let it go through an expansion process, right? Turn it back to very, very cold. As you reduce the pressure, temperature drops sharply, you see, right? Drop sharply until again 7.5, back to the same process. Then you channel it inside the room, you put it inside the room, it starts to absorb heat and boil. So this is the evaporation process. Then the thing goes back to the same cycle. Alright? So this is how the so-called refrigeration cycle in the pH diagram. Now we know the processes we need, right? We need to boil it, we need to compress it, we need to so-called like increase the pressure, increase temperature, all these things we know. So we need something, we need machine to help us do it, right? Like human, we cannot compress a refrigerant or something. So we need something help us to achieve this. That's why we have the four major components of air conditioner to achieve, to do the four processes that is needed, right? So here is an example of a like very typical component: compressor, condenser, expansion valve, evaporator. So this is the old one, the thermal expansion valve. This is the new one, the electronic expansion valve. So this will be the indoor unit. Here will be the outdoor unit, right? So the first component is the most important component, is the compressor. So in a traditional like a split aircon or the residential air conditioner, most of it is scroll compressor. We have a few type compressor, and this is a scroll compressor. You can see the animation here. This thing turns, and squeeze the refrigerant, right? So compressor is considered the heart of the air conditioning system, right? It's the one that press everything and move everything around, right? Compressor not moving, refrigerant not moving. So, and because this is the main like pusher or the pumper, something like that, it is the main power input. You consume the most power, right? And of course it's the most expensive part law. And one of the characteristics of compressor is it only can take in vapor, right? You cannot compress liquid. You only can compress gas, right? Right. So the second item is actually the combination of condenser and evaporator. Just now we said condenser, evaporator. Actually, they are heat exchanger, right? You put refrigerant, then it exchange heat with the air, right? I absorb the air, I release energy. So it is a heat exchanger. And again, the typical split unit is most of them is using the fin tube, like this kind of thing. And refrigerant goes in, travel, right? Then we have this aluminium fin act as a heat sink, like the fin, to increase the heat transfer rate, right? So you blow air through it, then refrigerant slowly, for example, if this is a condenser, you slowly condense, right? Actually, condense is start from above, then if it's evaporator, then it start to boil, right? Then go out, right? So, and when you transfer heat between refrigerant and the air, right? We use air, right? Like indoor unit, we transfer energy between the indoor air. Then we bring it outside. Again, we reject heat to the outside air. Everything is air. That's why it is called the air cool, right? Everything you dealt with air, so you call it air cool. We have the other thing is like the water cool, right? You reject heat to the water, right? But in this case, the simple one, the most common one, our house use one is the air cool heat exchanger, right? You call it air cool. Then the last one is the expansion valve, right? Expansion valve is a device that we use to control cooling capacity, right? It expands the gas, right? Release back the pressure, and it controls cooling capacity. And for example, like your hairspray, it just looks like hairspray, right? High pressure, then you spray it, become low pressure. So how much you squeeze the spray, equivalent to how you control the refrigerant volume and thus the cooling capacity. So now we have the entire four processes and four components to make this happen. The whole system is set up, right? Air conditioner, basically this is how it works. But now got two things that we need to bear in mind. The first thing is compressor can only take vapor, like we mentioned. And the second thing is how are we going to control cooling capacity? Like first thing is how we're going to make sure the compressor, because you see when during evaporation process, right? If how going to make sure that every time the evaporation process is 100% is complete, right? How are we going to make sure it? And when when the refrigerant goes into a compressor, it is 100% gas, right? We need to make sure these things. Then the second thing is we need to control cooling capacity. It cannot be like keep ramping, right? Like modern air conditioner, we can control the cooling capacity. So the first thing we use is the superheat, right? We use superheat to ensure 100% evaporation. Okay, what does it mean by superheat? Basically, superheat is absorbing heat after evaporation process. Imagine you have a refrigerant and the way you design is this is the amount of evaporation process. Like from here until here will be 100% evaporation. Beyond here, you superheat it for a little while before you let it enter the compressor, so that we have the buffer to ensure that everything turns into gas before entering the compressor, right? Because sometimes you have different cooling load, right? You have like your fan slowing down or dirty filter here and there. This thing will affect the air conditioner works in reality, right? So engineer, we all put some buffer, we call it the superheat, so that we ensure every time is 100% evaporation, right? So no liquid will be entering the compressor. So now we take this thing back to the pH diagram. We can see from here is evaporation process, up until here is 100% evaporation process. Done, right? Everything turns into vapor. But now, here is the buffer point, buffer range, right? The superheat region, right? We superheat for a while, then we let it go through a compression process. Then condensation, also same. Subcool is why we need subcool? Like the same principle applies. Like we make sure that we turns 100% liquid into 100% gas, right? Now during the heat rejection process, we need to turn everything back to liquid as well. You see, when you left with the gas inside the system, that means you are basically absorbing this amount of heat. You bring it outside, you bring back the same heat, right? We don't want that. We want everything throw outside, then come back in 100% liquid, so that the cooling capacity is maintained. If you don't have 100% condensation, your cooling capacity will reduce, right? That's why we introduce subcooling, right? Maybe one of the ways we slightly oversize the condenser outside. We subcool it, like we encourage the refrigerant to like you keep on reject it, like reject more. It's okay to drop some temperature, reject more. So subcool. The thing comes back, we know it is fully ready, 100% capacity, ready to absorb heat, right? So right here is just now we talk about expansion valve. How expansion valve can cool, can control capacity, right? So just now we talk about superheat is how we ensure the compressor won't get damaged. 100% gas will go in. Now is expansion valve. One of the way to control cooling capacity is to rely on the superheat temperature. What does it mean? Meaning that, for example, we design the superheat temperature, we want the refrigerant vapor, refrigerant gas to heat up, for example, 8 degrees Celsius more before you go into the compressor, right? This is what we design, right? What if the superheat temperature is below 8 degrees Celsius? What does it mean, right? Below 8 degrees Celsius, that means it's lower than what we expected. Meaning, it didn't enter superheat process as much as we expected, right? It delayed the process. That means the phase change process is longer than we expected. the evaporation process is longer. What do you mean by longer? That means you have too much refrigerant, or you have not enough cooling load, not enough heat for the refrigerant to absorb. That's why the boiling process is very long. Like for example, you boil water, right? If you put in small heat, the boiling process will be very long, right? So it's the same here. If you extended the evaporation process, you are not going to go into the superheat region as you expected. That's why the superheat temperature reduced, right? So in this case, the expansion valve detected, oh, now you are below 8, below what I want you to be, right? So I will reduce the refrigerant. Expansion valve will reduce refrigerant, then the thing balance back the refrigerant amount, the amount of refrigerant, and the heat inside the room will balance out. So the evaporation process will go back to the normal length, so to say, and it enters the superheat as you expected. Then you heat it up until you reach the 8 degrees Celsius, what you design. So that's how expansion valve control cooling capacity. If, for example, your superheat is too high, also the same, right? It will control accordingly. So we just say subcool, right? Ensure 100% condensation so that no cooling capacity is wasted. Alright? So that's about it. Thank you.